Okay, so now let's read some phase angles here. I'm still going to use the signal generator that I was using before, and okay, so use the same oscilloscope here. Input, okay, output, output is connected here as well. I think I should be able to see something here. Let's see. Okay. Oh, it was unknown. Okay. Now, my input is supposed to be sine wave. And my input is supposed to be a sine wave. And it's about 300 Hertz. It's about 300 Hertz. I don't see anything here. Oh, the input is disconnected. Okay. Where's the channel 2? Okay. Okay, so now you can see that at this frequency there is of course not much difference between the amplitude of the input and output, but the phase angle here is actually nothing. Okay, so now if I increase the frequency to around 500 Hertz, still the phase angle is not much. Actually, there is no phase angle at this frequency. Even up to 1 kHz, there is no phase angle. Okay. Now at 2 kHz, still no phase angle. At 3 kHz, no phase angle. At 6 kilohertz, still no phase angle. At 10 kilohertz, no phase angle. At 20 kilohertz, no phase angle. No phase angle. At 100 kilohertz, no phase angle. And it's starting to, the phase angle is starting about somewhere about here, somewhere about 100 kilohertz or so. So right here you see, this is my output. This is my output, and still I have no noticeable phase angle here. Of course. Okay, so then if I move to, for example, to 200 kilohertz, a little bit of phase angle. At 300 kilohertz, a little bit of phase angle. At, you see, at 400, 500 kilohertz, at about the phase angle starts at about 100 kilohertz, and goes all the way up to, and you can see what happens here. You see, as I'm increasing the frequency, the phase angle is increasing. Okay, and that's now I'm at 100 kilohertz times 10, which is equal to 1 megahertz or so. And then I go to, this is I'm at 1 megahertz. At 2 megahertz, the phase angle is a lot more. You see. So you see over here, this is your phase angle. You see over here, this is your phase angle. So move this down here and move this down here to make sure the phase angle is this is my input, this is my output, and this is my phase angle. Okay, so if I decrease the frequency, I think the phase angle is decreasing. So that's basically your phase angle, and it's interesting that the phase angle starts at 100 kilohertz and goes and keeps increasing as you increase the frequency. So for example, at for example 8 megahertz or so, you see this is your phase angle. So this is your input over here, and this is your output over here, and if I magnify this, you see what happens. So if I move this up here, you can see what happens. So now one of them is of course leading, one of them is lagging. You need to, but the oscilloscope is not showing me much at this high frequency, so I will simply basically increase the intensity, and so to find out which one is leading, which one is lagging, to actually it's not triggering on anything, so now it's triggering, but you can't see much. Now it's triggering. Okay, so this over here is your, and I'm at on the positive slope, negative slope. Okay, so my input signal is this one, and my output signal is this one. So my input actually is leading and my output is lagging. And the reason why I'm saying the input is leading, because you see this is the input. Okay, move the output out of the way. This is your input, and it gets to the peak at this point in time, right? Now your output gets to the peak at this point in time, meaning that your input gets to the peak much faster than this one, by basically 1, 2, 3 around by around 0.6 milliseconds. I'm sorry, by 0.6 microseconds faster than this one. So that's basically that. So your input is leading, and I'm at about 8 megahertz or so. Okay, and if I move the input up here, you see right here you can, although the wave is actually, I mean, let me move to, for example, 1 megahertz, because there I would be able to see much better from this signal than this one. Okay, now this is actually much easier. Okay, so now this is my input, this is on my output, and this is the phase difference that you can see over here. So this is the phase difference. The difference between these two peaks over here is the phase difference, or the difference between these two basically bottom peaks over here, or these two troughs over here, is the phase difference. So you can see that basically, since this is my input, the input is getting to the peak basically much faster than my output, although I was over times 10, and everything was being magnified. So I move it over here, but still doesn't really matter. So your input is basically getting to the peak much faster than the output, and the difference is about, if you move this thing over here, is about 0.8 horizontal units. 0.8 times is about 1.6 microseconds. By about 1.6 microseconds. The calculation that I did earlier is actually wrong, because I was magnifying everything by times 10. So I should have actually, I didn't know that I was magnifying. So that's basically your peak difference. Now I'm going to come back in a few moments, and note these down and do a few calculations. Let's see what we have here. We have a couple of things actually to cover. Okay, so now suppose I kind of suspect that the phase shift is also dependent on the voltage, or at least at some frequencies. Okay, I'm not really sure about this, but if you want to check whether the voltage, the phase shift is dependent upon the peak to peak voltage of your signal, what you can do is that right now you can see your phase shift over here. It's about whatever it is, it doesn't matter. So you want to check that. You can keep your signal at what it is. You don't have to change with that, but then you can play with the input voltage. So you see the input voltage is changing, and with that is changing the output voltage. But the phase shift is actually not changing much. You see, the phase shift is the same thing, so it's actually the same thing here. So if I move this thing up here, you see still I can see the phase shift over here, and this is my input, this is my output, and a little bit bigger, and still the phase shift is there, and it's not changing with the voltage, so it's not dependent on the voltage. So I change this thing to this view so that I can see everything, and then this is my output, and you see that the input is leading the output, and then the phase shift, if you want to read it on here, it's basically you basically need to, for example, move this thing to the middle of the screen. The peak of the signal, you move it to the middle of the screen, and then you can see that the so this is basically, for example, let's say that this is the basically this is the, if you take this as this is your input, right? So if this is your input and this is half of your cycle is happening in around 2.6 horizontal units or so. 2.6 horizontal units over here. Around 2.6 horizontal units. Okay, so half of your input signal is occurring in 2.6 horizontal units. Okay, so I apologize for this thing. So that means that your full cycle of your input is occurring in so one cycle is occurring in half cycle was 2.6. 2.6 times 2 is equal to 5.2 horizontal units is one complete cycle, and 5.2 horizontal units times the time base is equal to, and your time base is 0.2 microseconds. 0.2 microseconds. That means that one complete cycle is happening in 1.04 microseconds. 1.04 microseconds. Okay, and 1.04 microseconds. Now and if and basically what that means is that I'm sorry, I have to start over. So you want to calculate the phase shift. Basically the phase shift is half of the cycle, a half cycle of this input wave is occurring in 1.26 horizontal 1 point. My brain is not working right now. So basically what this is, half cycle is occurring in 2.6, half cycle in 2.6 horizontal units. Okay, so that means that a full cycle is occurring in 2 times that. So 2 times 2.6 times 2 is equal to 5.2 horizontal units. That means that 5.2 horizontal units corresponds to 360 degrees. Okay, so that's basically what you're looking for. 5.2 horizontal units corresponds to 360 degrees. Now the difference between the peak of the top of this, the peak related to your output signal, which is basically this one, and the top of this peak over here, which is your input signal, is basically right over here, is about 0.7 horizontal units. So the phase difference is, the phase shift is 0.7 horizontal units. Now if you calculate 0.7, basically what angle 0.7 horizontal units corresponds to, that's your phase shift. So basically then we said that, if I bring you down here, if I said that basically 5.2 horizontal units corresponds to 360 degrees. So 0.7 horizontal units then corresponds to 0.7 times 360 divided by 5.2, which is equal to 48.46 degrees. X is equal to 48.46 degrees. So that's your phase shift at 965,000 kilohertz. So at F is equal to 965,000 kilohertz, 966,000 kilohertz. I'm sorry, 966,000 hertz. The input is leading the output by 48.46 degrees, and that's your phase shift. Okay, so that's basically that. Now if you let me disconnect all these things, I don't need them anymore for now, and I move this to normal so I don't get anything here. Now let me bring this camera over here, and we will do some calculations. Okay. Okay, so basically what you want to do now is let's go over the data that we have. Let's see what we have first, and then we will take it from there. So basically what we have is that you see from here, this is my input voltage, this is my output, this is my frequency, then this is my output voltage. And the input voltage was about 7 volts input, 7 volts output, 9 volts input, 9 volts output, 9 volts at these are the frequency 4, 8, 10, 12, and these are in hertz. So then 9 volts, 10 volts, up to 80 hertz, and the same thing keeps happening all the way up to 14 kilohertz, and all the way up to 200 kilohertz. And over here the output was slightly higher than the input, and this is something that has something to do with the inductor. Okay, so and then you go all the way up to 500 kilohertz. The input is 10 volts, the output is about 11 volts. 950 kilohertz, 10-12 volts. 1 megahertz, 10-12 volts. And that was the peak of that. That was the peak of this voltage, meaning that if you plot the output voltage versus the frequency all the way up to 1 megahertz, then the voltage was at peak, and then it started rising, falling down. So for example, at 1.5 megahertz it was at 9.75, at 1.8 megahertz it was at 7.5 volts, at 2 megahertz it was at 6 volts, half, basically 60% of the input voltage. And then at this was all the way up to 2 megahertz. At 2.5 megahertz I was at 3.5 volts peak to peak. At 2.9 volts, at 2.9 megahertz I was at 2.4 volts, and then I go all the way up to 10 megahertz here, and then the voltage goes down all the way up to 1.4, 1, 0.6, 0.5, 0.4, 0.2, and 0.2 volts peak to peak. So what that means is that basically what that means is that if you draw a graph of the output voltage versus frequency for this, you would get something like this. So let's say that this is, for example, 2, 4, 6, 8, 10, and 12 volts peak to peak. V of out, volts peak to peak, 2, 4, 6, 8, 10, 12, and then this is frequency all the way up to 10 megahertz. I'm supposed to do a logarithmic scale here, but I'll do a simple scale here. So and the important points over here are at about 500 kilohertz. 500 kilohertz. So let's say that this is 10 megahertz. At 10 megahertz, and then this is, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, this is 10 megahertz. And let's say that at 500 kilohertz, so up to here, the input was, let's take these as all the full output or full input. So at about 500 kilohertz, which is 500 kilohertz, which is right here, and this is 1 megahertz. Okay, at 500 kilohertz the voltage started rising. So all the way up to here I was at 10 volts. I was at 10 volts over here, and then over here it started rising to 12. So at this point I was at 12. At 500 kilohertz I was at 11 volts. 11 volts. At 951 megahertz I was at 12 volts. And 1.2 megahertz, 1.5 megahertz I was at 1.2 megahertz I was at 12 volts again. And at about 1.5 megahertz I was at 10 volts. Okay, so that's basically something like this. And then at 1.8 megahertz I was at 7.5 volts. So this is 8, this is 6, 7.5 would be over here, and at 1.8 megahertz 7.5 volts would be somewhere over here. At 2 megahertz I was at 6 volts, so this is 2, 1, 2, 3, 4, 5, 6, let's say this is 7 for example, 8, 9, 10. Okay, so at 2 megahertz I was at 6 volts, which is right here. At 2.5 megahertz I was at 3.5 volts. At 2.5 megahertz I was at 3.5 volts, somewhere over here. At 2.9 megahertz I was at, or let's say take it as 3 megahertz, I was at 2.4 volts. So this is 2, somewhere over here. And at 4, basically at 4 megahertz I was at 1.4 volts. So this is 1.4 would be over here. And at 5 megahertz I was at 1 volt peak to peak. At 6 megahertz I was at 0.6. At 7 megahertz I was at 0.5 over here. At 8 megahertz I was at 0.4. At 9 megahertz I was at 0.2 and 0.2. So this would be the graph of the output voltage versus frequency. Okay. Okay, so that's basically that. That's basically that. And at this region between 500 megahertz to 1.5 megahertz, I suppose, we were above the input basically voltage. So that's basically that. Okay. So now let's calculate a couple of values here and get the hell out of here. So I want to calculate the things that I want to calculate is first the phase shift and a couple of values over here, and then that's basically all that I wanted to do here. Okay, so basically, for example, basically first of all, the circuit that I had was a low-pass filter, which was this thing over here. This was my input signal, this was my output signal, and we got kind of the same. We got kind of the same graph over here. At high frequency, at low frequencies, I had much of my input, and then at high frequencies the input started decreasing. Okay, so now for example, let's say that you want to calculate your V of out here at, so for example for this input, for example, let's say that start over here, so somewhere over here. So here my input was 10 volts at 14 kilohertz. My input was 10 volts, my output was 10 volts. So if frequency is equal to 14 kilohertz, and if V of in is equal to 10 volts peak to peak, if V of out is equal to 10 volts peak to peak, of course we are going to calculate this, or we can simply take these as true and then calculate, for example, the inductance of our inductor. That we can do as well. Okay, so 10 volts peak to peak, the value of the resistor that I had was 988 ohm. R is equal to 988 ohm, and I guess that's it. So now if you want to calculate the output over here, the voltage across this resistor, V of out is equal to basically the resistance of that resistor by the impedance of the circuit times V of in. Okay, so now I know that my input voltage and output voltage were the same at this frequency, 10 volts and 10 volts. So that means that R to Z is equal to V of out to V of in, V of out to V of in. And both of these were 10 volts to 10 volts, so this is 1. So R to Z is equal to 1. That means that R was equal to Z at this frequency. At this frequency, R was equal to Z. That means that the resistance of this resistor was actually equal to the impedance of the whole circuit. That means that the impedance of the reactance was of the inductor was actually 0, right? So that must have been 0, or not 0, actually equal to basically 988 ohm. Now I know that my resistor was 988 ohm, so that means that my impedance was 988 ohm. And so what is the impedance in this circuit? the impedance is equal to the square root of x of L squared plus R squared. And x of L squared is equal to, x of L is equal to 2 pi FL. Okay, so that means that Z is actually equal to the square root of this whole thing squared, so that is 4 pi squared F squared L squared plus R squared. Okay, but your Z was equal to 988. So now if you want to calculate your L here, you have to basically raise both sides of this equation to power 2, so that you can get rid of this thing over here, this radical sign. So now that means that Z squared is equal to 4 pi squared F squared L squared plus R squared. Okay, and you want to find out what L is, so that means that 4 pi squared F squared L squared is equal to Z squared minus R squared, and that means that L squared, let me write it here, that means that L squared is equal to this whole thing, Z squared minus R squared over 4 pi squared F squared. 4 pi squared F squared. And what that means is that your L is equal to the square root of Z squared minus R squared over 4 pi squared F squared. Now, of course, you can use some algebra to simplify this probably. For example, a squared minus b squared is equal to a plus b into a minus b. But it's not necessary, really. You can write this as L is equal to the square root of Z squared minus R squared over the square root of 4 pi squared F squared. And this is equal to the square root of Z squared minus R squared over 2 pi F. That is equal to L. So your L is equal to 1 over 2 pi F times the square root of Z squared minus R squared. Okay, so that is that. So you can use this formula if you know that the input voltage, the output voltage, or actually if the input and output voltage are equal, then you can use this formula to basically calculate your inductor, the value of the inductance. Meaning that you have to, I mean, the test circuit that you could make is that you can make a low pass filter and keep the frequency relatively low, something around the same frequency that we had here, about 14 kilohertz or so, and then find some spots on your oscilloscope screen. You can find some spot where the input and output voltages are exactly the same, and then if that's the case, then you can use this formula in order to find out what the inductance is on your inductor. So now if you want to do that, you can calculate your L as 1 over 2 pi, and the frequency was 14 kilohertz, times 14 into 10 raised to the power 3 hertz, times the square root of Z squared. Now Z squared you need to calculate. Z squared you need to calculate, and that is and for that you need to also calculate your X of L. So let me calculate that somewhere else and then bring everything over here. So in this circuit, X of L, the reactance of your inductor, was equal to 2 pi FL, which is equal to 2 pi the frequency times 14 kilohertz, 14 into 10 raised to the power 3 times L. Okay, so it gets a little bit more complicated actually, because right now I don't have the L over here, right? Okay, so we will find some way. I'll have to play with this a little bit and find some way in order to find the inductance of this inductor. Let's go back to one of these calculations, and I want to, for example, go over here for this frequency, which was the peak, and calculate my output over here, for example. That would be interesting. And let's actually see if that actually happens in calculation as well. So let's see if that actually happens in calculation as well. So let's say that your frequency F was basically 1 megahertz, and your input voltage was 10 volts peak to peak, and this was V of in. You want to calculate your V of out. Your resistor was 900, what was it, 988 ohm. 988 ohm. Take it as 990 ohm. 990 ohm, and that's basically that. And I take the inductance of this inductor as 100 microhenry. It's written on the inductor. I'm not sure if that's how much tolerance there is in this value, but I take it as 100 microhenry. L is equal to 100 microhenry. Okay, so now your V of out for that circuit, V of out, is equal to the resistance of that resistor over the impedance times V of in. So the only thing that you need to calculate is your impedance, and so your impedance is the square root of X of L squared plus R squared, and for that you need X of L. So X of L is equal to 2 pi FL, which is equal to 2 pi times the frequency, which was 1 megahertz, 10 raised to the power 6 hertz, times the inductance, which was 100 microhenry, 100 into 10 raised to the power negative 6 Henry. So these two will cancel out, and that's equal to 200 pi. That's 200 pi. So your X of L is equal to 200 pi. 200 pi is the same thing as about 600 ohm or something. Over 600 ohm. So now V of out here is equal to R to Z, which is equal to, R was 990 ohm, 990 over 200 pi. Oh, sorry. No. I'm making a mistake here. Z is equal to this thing. Sorry. Z is equal to the square root of X of L squared, which is 200 pi squared, whole squared, plus R squared, plus 990 squared. And that's equal to the square root of 200 pi squared plus 990 squared. That's equal to 1172.6. 1172.6 ohm. So your Z is equal to 1172.6 ohm. That's also in ohm, basically. Okay. Now 1172.6 ohm. That's your Z. So your V of out is supposed to be equal to R, which is 990 over Z, which is 1172.6 times V of in. And it's not going to give me 12 volts. It's equal to, V of in is equal to 10 volts. It's going to be somewhere below 10 volts. 990 divided by 1172.6 times 10 is going to give me 8.4 volts. 8.4 volts peak to peak. But my output was actually at 12 volts. Okay, so that's something weird that happens because of the inductor, and we will have to see more about that later. But now let's go and calculate some other value. Let's go calculate some other value. So let me get rid of these things over here. So this is my output. Let me get rid of these as well. Okay. And this is the data that I have. So this is my circuits. And these are the kind of things that I don't. Oh, this is the circuit that I have. I want to get rid of these things. Okay, so now I will end this video here. In the next video we will do some more calculations with this circuit. So I'll see you in the next video.